Dear students, today we will discuss about fundamentals of flat plate collectors. Okay? So, what is solar collectors? The solar collector is a device to collect solar energy and transform it into thermal energy by using heat transfer fluid like water, air or ethylene glycol. So, when the ambient temperature goes below 0 degree C, then we have to think of some other material like water with ethylene glycol in order to make it operative. The solar thermal system provides thermal energy for various processes. For example, if we consider cold climates, the low grade thermal energy is required to heat air for comfort, hot water for washing, cleaning and other domestic and industrial needs. Okay? And even in high temperature heating applications, a significant amount of fuel can be saved by using solar collector for preheating. Of course, it has got plenty of applications like drying and any other agricultural field. So, how these solar collectors can be classified? Majorly, there are two categories. First is non-concentrating type and second one is concentrating type. Okay? So, flat plate collectors, that may be liquid flat plate collectors or maybe air flat plate collector, this will be under non-concentrating type. So, under concentrating type we will have two classes, focus type and non-focus type. Then in under focus type we will have again two more classes, line focused, that is single tracking, and point focus systems where two axis tracking is mandatory. Okay? So, example of line focus systems are cylindrical parabolic concentrator, fixed mirror solar concentrator, then linear Fresnel collector. Okay? And under point focus systems we will have parabolic disc collector, then hemispherical bowl mirror concentrator, then circular Fresnel lens concentrator and central power tower or central tower receiver system. Okay? And under the class of non-focusing systems we will have two categories, then modified flat plate collector and compound parabolic concentrating type collectors. Okay? So, this is how solar collectors are classified. We will learn with time the difference between these two and then which one is important and what condition, what type of collectors can be utilized for harvesting thermal energy. Now, if we briefly compare between concentrating type and non-concentrating type collectors, then what are the differences? So, under concentrating type collectors, the solar radiation is converged from a large area into small area using optical means. So, this will be something like we will have this large area and absorber will be here, solar radiation will fall here and it will reflect here. So, this part is absorber. Okay? This part is absorber and this will reflect, okay, a reflector. Okay. So, solar radiation first strike on this reflector and is goes back to this absorber. Okay. So, concentrated solar radiations are used here. So, beam radiation which has got unique direction and travels in a straight line can be converted by reflection or refraction techniques. Okay. So, in case of concentrating collectors only beam radiations are applied. Okay. So, diffuse radiations cannot be applied because it has no defined direction, what I should say. So, it will come from different directions and intensity is lower. Okay. So, this diffuse radiation has no unique direction and so does not obey optical principles. Okay. So, these diffuse components cannot be concentrated, that we should keep in mind in case of concentrating collector. Also, these concentrating collectors make use of beam radiation component and little diffuse components coming directly over the absorber. So, there are some radiation which comes from sun and it strikes on the absorber. So, these components are used, but no amount of contribution for heating effect for this diffuse radiation is very less. The primary advantage of this concentrating collector is high temperature can be attained due to concentration of radiation, which yields high temperature thermal energy. Okay? And in case of non-concentrating collectors, both beam as well as diffuse radiations are utilized. Okay? So, here this is one advantage. Okay? So, both the components can be applied for generation of thermal energy, right. So, if we talk about flat plate collectors, a flat plate collector is simple in construction and does not require tracking. So, which is under non-concentrating type. Okay. So, it can properly secured on a rigid platform and thus become mechanically stronger than those requiring flexibility for tracking purposes. That is obvious now. These collectors are installed outside or outdoor applications, and these are exposed to atmospheric disturbances like rain, storms and any other that kind of disturbances. Okay. So, mechanically there has to be stronger. Now, there are three primary performance indices in case of flat plate collectors. These are collector efficiency, concentration ratio and temperature range. Okay. So, what is collector efficiency? It is defined as the ratio of energy actually absorbed and transferred to the heat transfer fluid by the collector. Okay. So, this is nothing but useful energy to the energy incident on the collector. So, that means, so we have this absorber. So, we learn the different components. So, we will have glass, then we will have absorber, then some tubes will be there. Okay. So, the heat transfer fluid will flow through these tubes. Okay. So, as you can understand, by analyzing this collector efficiency, how we can define it is the energy actually absorbed and transferred to the heat transfer fluid by the collector. Okay. So, here how much energy is transferred to the amount of radiation which is falling on the collector. Okay. Maybe I if we and A, and this may be Q is the useful energy. So, this will be something like Q by I into A. Okay. So, this is how this efficiency can be defined. Okay. And then next important parameter is concentration ratio, which is defined as the ratio of the area of the aperture of the system to the area of the receiver. Okay. The aperture area of the system is the projected area of the collector facing the beam. Okay. So, this is something like this is the aperture area, okay, and this is the absorber. Okay. So, this area A and this is small. So, A by A is something called concentration ratio, right. So, for example, this concentration ratio for a flat plate collector is 1, because this area for flat plate collector. So, amount of energy received here, okay. So, same amount of energy is flows to this part. So, this area is fixed. Okay. So, because of that we will have concentration ratio for FPC is 1. Okay. And since more area is exposed, then losses will be more. Because of that we cannot get the temperature more than 100 degree Celsius. Okay. This concentration ratio for line focus system may go up to 100, okay, and its temperature varies from 150 to 400 degrees C. So, that much of heat can be generated by making this kind of collector. Okay. And then if we are interested for very high temperature application, then concentration ratio should be very high. It is in the order of 1000. Okay. So, we can go up to temperature of 1000 degrees C. Okay. So, we will study this more extensively when we study concentrating collectors. And the third category of performance indices is temperature range. So, this range of temperature to which the heat transport fluid is heated up by the collector. Okay. So, this temperature range also important, and by knowing this temperature range we can classify what kind of collector is required to get that particular temperature. Okay. So, these indices are important to characterize a collector. Okay. Now, come to the construction of a flat plate collector. Okay. So, as far as construction of a flat plate collector is concerned, it has got 4 primary components, that is absorber plate, then tubes fixed to the absorber plate, okay, transparent cover, then collector box. Let us have a look on the sectional view of this flat plate collector. Okay. So, this is the outer side, and here the top side will have glass cover. Okay. So, here 2 glass covers are shown here. This is the glass cover 1 and this is the glass cover 2, and this is the absorber plate, and you can see the tubes, these are tubes. Okay. So, here what happens, same sheet is used and then extruded. Okay. So, material of construction is same for both tube and sheet, right. So, this is an absorber plate and these are the tubes through which heat transfer fluid flows, okay, and we have to provide sufficient insulation to reduce the heat losses, okay, and finally we need to provide a casing to hold the entire structure, right. So, this is all about the construction part, and here it shows the collector characteristics curve. Okay. In the vertical axis it shows useful power collected or energy collected, and here in the horizontal axis it shows temperature of plate above ambient. Okay. So, this P is for plate temperature or absorber plate temperature, and TA is the ambient temperature. Okay. This temperature difference once we know, and we know the other characteristics, then we can plot this curve for a flat plate collector. So, what does it mean? So, amount of energy what is falling on the glass is not received by the absorber plate. So, some losses will be there. So, what are losses? These are the losses. Okay. Because of the losses, so all the energy what is received by the glass cover cannot be converted to useful energy. Okay. And there are some losses with this glass and other factors. So, we will discuss all those issues step by step, okay, and what will be the material, okay, what will be the transmissivity, what is the reflectivity, all those informations are required to characterize completely this kind of flat plate collector. Okay. So, finally what happens, this collector is useful energy will be something like this. Okay. This part is the useful energy, right. Since solar radiation is varying, so this component will vary. So, finally we can have this kind of plot, right. So, advantages already we have discussed. So, it utilizes both beam and diffuse component of the solar radiation, and little maintenance due to simple stationary design. Okay. No moving parts, no mechanical components. So, it is a very good structure. But primary disadvantages are something like collection efficiency is generally low, and this is due to absence of optical concentration. Okay. And this area from which heat loss is very large. Okay. Because of that we cannot have high temperature application from this FPC collector. Okay. Now, let us have a look about the components. Okay. So, primary component is absorber plate, then tube, then we need header. Okay. So, in this figure this is an absorber plate and these are the tubes through which heat transfer fluid flows. Okay. And these are soldered here in this tube. Okay. There are different configurations, sometimes we can have this kind of configurations, okay. Then we can get this kind of configurations, and there are different kind of configurations are available. There are many manufacturers for this kind of flat plate collectors. So, this is the absorber plate which is the primary component of a flat plate collector, and we will have these tubes, okay. And these are the glass covers. Okay. There may be more than one glass covers, okay, and the direct radiation shows in the straight arrows, and this is the broken arrows. Okay. This is for diffuse radiation. Okay. And we have to provide sufficient insulation to reduce the heat losses. This is a sectional view of a flat plate collector to show the glass cover, then absorber sheet, then tubes. Okay. And this figure shows the tubes and headers. Okay. So, usually this absorber plate is made from a thin metal sheet, normally copper is used, okay, and thickness varies from 0.2 to 0.7 millimeter. Okay. And these tubes are also made of metals, and its diameter varies from 1 to 1.5 centimeter. Okay. And tubes are soldered or braced or pressure bonded to the bottom of the absorber plate. Sometimes it is also seen though tubes are attached at the top of the absorber plate. This kind of configurations are also available. Okay. So, these header pipes which lead the liquid in and out of the collector and distribute it to the tubes are also made of copper and have slightly larger diameter. Its diameter varies from 2 to 2.5. So, these two are the headers. Okay. So, cold fluid enters here and then it distributes through these tubes, and then hot fluids are collected here, and that can be stored, and this can be utilized based on the requirement. Okay. So, these are the headers. So, these tube diameters are slightly larger than these tube diameters. Okay. So, what is the role of absorber plate? Okay. So, primary role is to absorb the maximum possible solar radiation incident on it through the glazing. Okay. So, how this can be maximized? Okay. That is the first role of an absorber plate, and then to minimize the heat losses from the absorber to the atmosphere from the top, bottom and sides of the FPC. Okay. So, when we are talking about this, when solar radiation falls here and some losses will be there, then some amount of energy will be received in the absorber plate. This may be absorber. Okay. Then what happens? Some radiation will goes back. Okay. So, re-radiation will be there. So, this loss is normally high. Okay. This is the re-radiation part which is taking place from the top of the flat plate collector, and conduction and convection losses will be there from the sides and the bottom. Okay. So, from here conduction QC and then convection Q, CO and V, these losses will be there, and this is QR. Okay. Radiation losses. Since these losses are really very high, so we need to do something to reduce those losses so that we can maximize the collector efficiency. And also the third role is to transfer maximum heat to the fluid. So, these are the primary roles of an absorber plate. Okay. Now, let us see about cover system. The cover should be made of a material which is highly transparent to the incoming solar radiation and at the same time opaque to the long wave re-radiation emitted by the absorber plate. So, what I said, so this is the glass cover and then we will have this absorber plate. Okay. So, when it strikes and some of the radiation goes back. Okay. So, this cover system has to be designed in such a way that this radiation should be minimized. Okay. And normally for this cover system, toughened glass of 4 to 5 mm thickness is used. Okay. Of course, nowadays plastic transparent sheets are also available, which are used in many of the developed countries because of its low cost and lightweight, but we need to see the origin of the plastic. It is originated from fossil fuel. So, it will contribute to greenhouse gas emission. So, that way we need to think the kind of material to be used for a particular application. This glass is able to withstand thermal shock as well as the impact on objects which may fall on the collector face. Okay. Normally, a gap of 1.5 to 3 centimeter is maintained between the cover and the absorber plate. So, this distance is something like 1.5 to 3 centimeter is maintained, okay, between this cover and then absorber system, right. And also we need to think the kind of insulations to be used to reduce the heat losses in the collector system, right. So, bottom and sides are usually insulated by mineral wool, rock wool or glass wools, okay, with a covering of aluminum foil. Okay. So, this thickness is about 2.5 to 8 centimeter, that thick insulation need to be provided, right, to reduce the heat losses. And then the whole assembly is contained within a box which is tilted at a suitable angle, right. So, that angle has to be fixed based on the location. Okay. The collector box is usually made of aluminum with a epoxy coating on the outside for protection. Okay. So, this kind of epoxy coating is also required. Okay. The face area of the collector are around 2 meter square with length. Okay. So, this is something like this is maybe 2, okay, and this may be 1. Okay. Width is smaller than length. Okay. So, this configuration 2 meter by 1 meter will be 2 meter square. Okay. So, this is a standard collector which is available in the market. How to position a flat plate collector, right? So, as we know, this is north, south, east and west, and we have to install the flat plate collectors towards facing south or due south, okay, so that we can get maximum exposure to the solar radiation, right. So, this is the collector and we need some kind of frame to hold the structure, okay. Maybe we need to do some kind of civil work here to install, and then we can collect the hot water from the storage bin here. So, that can be piped and then that can be utilized in day to day application. Okay. So, installation is made something like this and it has to be maintain some kind of tilt, okay, in order to maximize the solar radiation exposure. Okay. So, what are the different type of absorber plates available in the market? Okay. So, how this can be classified? Okay. So, these are classified based on extent of weighted area relative to the absorbing surface area, right. So, first configuration is the pipe and fin type, second one is water sandwich type and third one is semi water sandwich type. Okay. So, in case of pin and fin type, liquid flows only in the pipes. As you can see, these are the pipes through which this heat transfer fluid flows, right. There is no contact with the absorber plate, and this is comparatively low weighted area and liquid capacity, right, and applications in domestic and industrial use, because high temperature can be generated by using this configuration, and this can be used both in domestic and industrial applications. In case of rectangular or cylindrical full sandwich, both the weighted area and water capacity are high, okay, and it can be applied in warming of swimming pools, because it can generate low temperature fluid. Okay. And final configuration is roll bond or semi sandwich type, and this category is intermediate between pin and fin type and rectangular sandwich type, and temperature also in between these two configurations, right. So, these are different configurations are available in the market. So, based on the application we can select which one is appropriate for the particular application. Now, come to the performance analysis of a flat plate collector. Okay. So, while analyzing the performance, we must pay attention to the energy balance on the absorber plate under steady state condition. Okay. So, if we are interested to develop this energy balance on the absorber plate under steady state condition, so we will get something like this. QU is equal to AP multiplied by S minus QL. Okay. What is QU? Is the useful heat gain. Okay. This is nothing but the rate of heat transferred to the working fluid. Okay. So, we are interested about this QU only, right. So, how to maximize this QU, right. So, if we minimize this QL, then we can maximize it, okay. And if we can maximize this S, then we can maximize this QU. Okay. So, we will learn how this QL can be calculated and how we can minimize this QL losses, and how this S can be maximized to get more useful heat gain. Okay. So, what is S? Is the incident solar flux absorbed in the absorber plate. Okay. So, we have glass cover and absorber plate. So, we are talking about S. Okay. So, when solar radiation is coming from the sun, so we will say IT, the amount of solar radiation received by the glass cover is different than the amount of solar radiation received by the absorber plate. Okay. So, IT is different than S. Okay. We need to maximize the S, right. And AP is the area of the absorber plate. Okay. This is the area of the absorber plate. So, this will be something like this, right. So, this will be something like this because okay. So, area, so this kind of system it will be. So, this is the area of the absorber plate, not the collector, or it is just the inside absorber plate. So, when we talk about collector, so this will be AC. Okay. It includes those glass cover. Okay. So, normally this AC is about 1.2 times AP. Okay. So, this AC is actually 1.2 times of AP. Okay. So, normally it is specified, and QL is the rate at which heat is lost by convection and re-radiation from the top surface and by conduction and convection from the bottom sides. Okay. So, this need to be critically analyzed, okay, to reduce the heat losses. So, if we are interested about the flux incident on the top cover of the collector, then how to calculate it? So, this IT already we have done the derivation of this expression in the earlier classes. So, this IT is equal to IB into RV plus ID into RD plus IB plus ID multiplied by RR. Okay. So, this is known to us, and this gives this IT the amount of radiation which is falling on the collector, right. So, now we are interested about the flux absorbed in the absorber plate. Okay. So, for S, okay, now is for S. So, if we are interested for S, then what we need to do? We need to multiply this expression with tau into alpha for beam radiation, then tau into alpha for diffuse radiation. As we know, this flat plate collectors utilizes both direct component as well as diffuse component of the radiation, right. So, both the things we need to consider here. So, this tau alpha B is the transmissivity absorptivity product for beam radiation falling on the collector, and tau into alpha D is the transmissivity absorptivity product for diffuse radiation falling on the collector. Okay. So, in order to calculate S, we need to understand what is tau and what is alpha for beam and diffuse radiation. So, we must know this, then only we can calculate S, and then we can calculate QU. Of course, we need to know what is QL. Okay. Let us learn how to calculate this tau alpha B and tau alpha D, right. Now, this transmissivity of the cover system. So, we are talking about this cover system only. Suppose two glass covers are here. So, glass cover 1, glass cover 2. Okay. So, we need to see how these radiations are behaving and what will be the transmissivity of the cover system. Okay. So, without knowing this transmissivity, we cannot calculate this S, or amount of flux received by the absorber plate, right. So, this tau is a function of tau R and tau A. What is tau R? So, this is transmissivity obtained by considering only reflection and refraction. Okay. So, we need to rely on Snell's law, right. And this tau A is transmissivity obtained by considering only absorption. Okay. So, in order to find out this tau, then we need to use Bogart's law. Okay. So, when we are interested for transmissivity based on reflection and refraction, we will use Snell's law, and when we are interested for transmissivity based on absorption, then we will use Bogart's law. Okay. And these laws are applied for both diffuse and normal radiation, right. So, at what condition we can consider the tau value for diffuse radiation once you know the tau value for normal radiation at different incidence angle, right. Now, let us learn what is Snell's law. Okay. So, if we consider a beam of light what is striking on the interface, so this may be one medium and this may be other medium, maybe this is air or this may be glass for our case. Okay. So, this beam strikes on this interface at an angle theta 1, this is the angle of incidence, and this direction of the reflected beam can be demonstrated by this theta 1, which is angle of reflection. Okay. So, theta 2 is the angle of reflection because of this refractive indices. Okay. So, this direction of the incident and the reflected beams are related to each other by Snell's law. Okay. How can we define this Snell's law? Sin theta 1, this sin theta 1 to the sin theta 2 is equal to n2 if we consider the reflective index of this medium is n2 and this is for 1, okay, n1 for this medium, then n2 by n1. This relationship gives, no, if we know this n2 and n1 and theta 1, of course, we can calculate what is angle of refraction, right. And this beam has got reduced intensity, okay, this IR, because this IBN strikes and then some amount of radiation goes in the other medium and then it is reflected, right. So, this reflectivity, that is rho, this IR, if we consider this is an IR and this is IBN, okay. So, this IR by IBN, that fraction of energy which is reflected is related to the angle of incidence and refraction by the following equations. Okay. So, this rho is something like 1 by 2, that is rho 1 plus rho 2, that is average of rho 1 and rho 2. What is rho 1 and rho 2? These are the reflectivities of two components of polarization. Okay. So, mathematically this can be expressed something like this: rho 1 is equal to sin square theta 2 minus theta 1. So, theta 2 is the angle of refraction, theta 1 is the angle of reflection, and sin square brackets theta 2 plus theta 1. Okay. And for the second component we will have tan square theta 2 minus theta 1, tan square theta 2 plus theta 1. Okay. So, these are the reflectivities of two components of polarization. So, if you are interested to know about the polarization, please refer some standard books to know how polarization happens. For a special case, if theta 1 is 0, if this beam of light is incident normally and theta 1 is 0, okay, then under that condition what will be the rho? Rho is equal to rho 1 rho 2, or two components of polarization will be n1 minus n2 divided by n1 plus n2 whole square. This is the expression. And similar analysis can be carried out for transmissivity, okay, tau r, okay, which is nothing but average of tau r1 plus tau r2. Okay. What is tau r1 and tau r2? They are transmissivities of two components of polarization. Okay. So, this information is very, very important while calculating tau. First we must know tau r, then tau a, then finally we will calculate what is tau. Okay. Now, in continuation, the considering one component of polarization of a beam incident on a single cover. Okay. So, here only single cover is used. So, this as a whole this is a glass. Okay. So, there are two interfaces, interface 1 and interface 2, okay, and there are multiple reflection will takes place. So, if we consider a beam of light, when it strikes on this interface 1, it is reflected, some amount of radiation will goes to the atmosphere and then some amount will travel through this glass cover. Okay. And when it strikes this interface 2, some component of radiation will again reflected and then some component will goes back to the atmosphere, okay, and some component will be transferred to the absorber. So, absorber will be here. Okay. So, this will continue infinitely, right. So, if we add these components, okay, amount of transmitted energy which is going to strike in the absorber, we can add all those components, okay, and we can sum it, and what will give this expression we will get 1 minus rho 1 to 1 plus rho 1, right. Similarly, we can do it for the other component of polarization, it will be something like this 1 minus rho 2 by 1 plus rho 2, right. So, this is a case for single cover. Okay? This is a glass cover, interface 1, interface 2, and this many things are happening inside this glass cover. Okay? If there are more number of glasses, then situation will be different. Okay? So, under that condition, we need to use these two expression, okay, for tau r1 and tau r2. Okay? So, what difference is? That is, m is the number of cover. Okay? So, number of cover system, maybe 2 cover, normally 2 covers are optimum if selected coatings are not applied. Okay? We will discuss what is selective coating, what is the importance of selective coating. If we apply selective coating on this observer plate, there is one glass cover is enough to harvest sufficient amount of energy. So, now come to the transmissivity based on absorption. Okay? So, this is obtained by assuming that attenuation due to absorption is proportional to local intensity. Okay? So, which law tells about this? It is a Booger's law. Okay? So, this is something like di is equal to minus k multiplied by I into dx. If we consider this configuration where normal radiation is falling perpendicular to this plate, okay, then what happens? That we will discuss. Oh, of course, we will discuss when no solar radiation falls at certain angles, then what happens to this configuration. So, both the case we will study one by one. So, what is K? K is the constant of proportionality and also called extinction coefficient, which is independent of wavelength. Okay? And if you consider this cover system and thickness of the cover, if we consider delta C, and if we take a small section here in between this cover system having no thickness is dx, and the I is the amount of radiation what is striking on this side, and other side is I plus di. Okay? So, if we rearrange these values like di by I for our own purpose minus k into dx, and if we integrate from IBN to IL, okay. So, what we will get? We will get this kind of expression, and finally, we will get this, and then we will have IL by IBN is nothing but tau A, which is equal to exponential of minus k into del C, right. So, this extinction coefficient is property of the cover material, right, but it is independent of the wavelength, and its value varies from 4 to 25 for glass. Okay? So, lower value is always desirable for this kind of applications, because it will give more transmitting rays. Okay? So, here what happens? This is the incident beam intensity, and IL is the intensity of outgoing radiation. Okay? So, we can relate these two and we can find out what will be the tau A, that means transmissivity based on absorption, right, when the beam radiation is falling normally. Okay? So, if the beam radiation is falling at certain angles, then what will happen to the expression of transmissivity due to absorption. Okay? So, our exercise goes something like this: when the solar beam is incident at an angle of theta 1. So, this is the angle of incidence theta 1 with the normal to the horizontal surface, and the path travel through the cover would be. So, this is theta 2 is the angle of refraction, right. So, this thickness is delta C, already we know, and this is the length. If we point this as A and this point may be B. So, what we can write A B, this cos of, if this is theta 2, this is also theta 2, okay. Cos of theta 2 is delta C. So, A B will be delta C by cos of theta 2, right. So, we use that same equation di by I is equal to minus kx, and we integrate both the sides. Okay. Now, distance will be 0 to delta C by cos of theta 2. Okay. So, if we do the integration, so we will get something like this, and di by I is ln of y from IBN. So, this from IBN, this is IL. So, integrating is from IBN to IL, and then minus k into x, okay, because integration of dx is x, it will vary from 0 to minus del c 2 cos of theta 2, and if we substitute there, then we will get this kind of equation. And if we are just to know about IL by IBN, then this will be something like exponential of minus k del c by cos of theta 2. Okay. So, this above equation is nothing but representing the transmissivity due to absorption when this beam radiation is falling at certain angles, okay, with the normal to the horizontal surface, right. So, this expression will be something like IL to IBN is equal to tau A, which is nothing but exponential of minus k del c by cos of theta 2. Okay. So, once you know this, we can also calculate tau, then rho, and then we can calculate the transmissivity of the cover system. So, this is R, okay, and this is tau, right. So, how this solar radiation propagates to glass window. Okay. So, if we consider this is a glass window and solar radiation is coming from the sun and it passes through this glass cover, and then what happens inside this collector. This is an absorber, okay, which is long wave radiation will come out once it strikes, and this is a absorber, this is a blackened surface, normally it absorbs the radiation. Okay. So, what happens, this phenomena is presented here. Okay. This is the energy which is coming from the sun striking on the glass cover, and then it goes inside the flat plate collector, and then long wave radiation emitted by the absorber, okay, and then it goes out some of the radiation from the glass cover. Okay. So, that is how it shows how the solar radiation propagates through glass window. Now, this transmissivity for diffuse radiation. Okay. So, what we have discussed so far, it was transmissivity for normal radiation. Okay. So, this diffuse radiation is equivalent to beam radiation coming at an angle of 60 degree. Okay. So, if this angle, so this is the system, and if this angle is 60 degree, okay, so then what we can consider, so it is a value for diffuse radiation. This angle is arrived at by considering the variation of transmissivity and assuming that the amount of diffuse radiation coming from all the directions is same. Okay. So, under that condition we can do this, okay, because it is very difficult to predict, because it has no direct direction. Okay. So, it is anisotropic. So, we can also plot this variation of tau r, tau a and tau for this example. Maybe if we can take glass, then number of covers, then thickness of each cover, then reflective index of glass relative to air is 1.52, extinction coefficient is 15. Okay. So, we can develop this plot by varying the angle of incidence. So, we can use the equations what we have discussed, and we can generate this kind of plot for tau, tau r and tau a. Okay. So, at this 60, so once we got this value here, so the radiations which is coming at an angle of 60 can be considered radiation value for diffuse radiation. Okay. So, let us do one exercise to strengthen our understanding how to calculate this tau. So, in order to calculate tau, we need to know what is tau r and tau a and those other components. Okay. So, taking the same problems and taking the angle of incidence 30 degree. So, let us now calculate what is rho 1. So, already we know what is sin square theta 2 minus theta 1, okay, and then sin square theta 2 plus theta 1, and rho 2 is 10 square theta 2 minus theta 1, then we have 10 square theta 2 plus theta 1. Okay. And also we know the tau r 1 and tau r 2. Okay. So, what is tau r 1 and tau r 2? 1 minus rho 1, then we will have 1 plus 2 m minus 1 into rho 1, and here 1 minus rho 2, and then 1 plus 2 m minus 1 is rho 2, right. Before that we must know what is theta 2. Okay. So, theta 1 is known to us, theta 1 is 30 degree, and in order to calculate theta 2, already we know sin theta 1 by sin theta 2 is n 2 by n 1, okay, by using Snell's law, and from there we can calculate what is sin theta 2 will be n 1 by n 2, okay. Then this will be sin of theta 1. Okay. So, if we substitute these values, so this is 1, this value is 1.52, and then we will have sin of 30. Okay. So, this will give theta 2 is something like sin inverse of this value once it is calculated. So, this value, this will give a value of 19.20 degree. So, theta 2 will be 19.20, right. So, now if we substitute this value here, theta 2 and theta 1, okay, theta 1 is known as 30, and then theta 2 we have calculated is 19.20. So, this value once we calculate, this will be 0.613, and this value is 0.0634. Okay. So, once we utilize this here, so in this expression 1 minus rho 1 is 0.613 divided by 1 plus how many covers? 2 covers are there. So, 2 into 2 minus 1 into 0.613. Similarly, we will have the value for tau r 2. So, this is 1 minus 0.0634. I think this is somewhat wrong. These values I think 0.0613, 0.0613. Okay. And now this is 1 plus 2 into 2 minus 1 multiplied by 0.0634, right. So, this value, and I can write here, this value is 0.786, okay, 69 I can write to be precise, and here it's 0.7928. Okay. So, this is for tau r 1, this is for tau r 2. Okay. So, once we know tau r 1 and tau r 2, then we can calculate what is tau r, okay, which is nothing but average of tau r 1 plus tau r 2, right. So, on substitution what we get, tau r value will be 0.7898. Okay. And now we need to calculate tau a. We know the expression tau a is e to the power of minus k m. Okay. We have delta, right, m is number of glass cover, and then we have cos of theta 2, right. So, this extinction coefficient is given as 15, and number of cover is 2, and then this delta c is 4 mm into 10 to the power of minus 3 if we have to convert it to meter. Okay. Then we will have cos of theta 2 already we have calculated, it is 19.19.20, right. So, this will give a value of 0.8807, right. So, this is tau a and this component was tau r. Now, immediately you can calculate what is tau. Okay. This tau is nothing but tau r multiplied by tau a. Okay. So, if we multiply both this term, what you will get is the transmissivity of the cover system. Okay. So, this is something like 0.695. Okay. So, we should not confuse about this m. M is the number of covers. Okay. So, in this case it is 2, that is why it is multiplied by 2, and it was given delta c was 4 mm. So, that is why it is 4 into 10 to the power of minus 3 meter. Okay. So, on substitution what we get is tau a, and finally, what we have calculated is tau. Okay. Its value is 0.695. That is transmissivity of the cover system, right. Now, let us also learn about transmissivity absorptivity product. Okay. So, which defines the ratio of flux absorbed in the observer plate to the flux incident on the cover system. Okay. So, if we consider a beam of light and it transmitted through this cover system, and maybe this tau what we have calculated now, this tau will introduce here and it will strike on the observer plate. Okay. Once it strikes on the observer plate, what happens? It is reflected. Okay. Some component will be absorbed here. So, this alpha will come here, some absorptivity will be there. So, what happens? We need to maximize this alpha. Okay. How to maximize it? Then we will discuss. Okay. Like we need to apply some kind of coatings here. Okay. So that we can maximize the absorptivity, right. And when it travels through this line, again it will move out from the cover system, some losses will be there, and from that again it will be reflected back to the absorber. Okay. Then it will absorb some component, and again it will reflect some component, and it will goes off from the cover system, and from that again it will come, and it will continues infinitely. It will continues infinitely. Okay. So, if we sum these values, then what we will get? That much of energy will be absorbed in the observer plate. Okay. So, that net fraction absorbed will be something like this. So, this component is common. So, we can take common from all the expression, and we can make this kind of summation, right. So, what is rho d here? So, this is a diffuse reflectivity. So, that has to be calculated. Okay. So, normally what happens, this diffuse reflectivity of the cover system is considered to be 0.21 if two glass cover systems are used, and 0.15 for single cover system if it is used in operation, right. And this rho d can be found by determining the value of tau a multiplied by 1 minus tau r for the cover system for an incidence angle of 60 degree. So, this is the procedure by which we can calculate what is rho d. Okay. So, once we know this rho d, then we can substitute here, and these values are known. Okay. This has already been calculated. This is the property of the material. Okay. What is used as the observer plate, and when some kind of coatings are applied, so we must know what is the absorptivity of the coating or selective coating. Okay. And this is known. So, we can calculate what is the net fraction of radiation absorbed in the observer plate, right. So, this is how we can calculate. Okay. And this we need to understand very carefully, then only we can feel how a flat plate collector can be designed and what is the complexity in designing a flat plate collector. Now, we must know two important parameters. One is instantaneous collection efficiency and other one is stagnation temperature. They are related, right. So, how do we define instantaneous efficiency? Means useful heat gain, as I have discussed this issue in the earlier slides. Useful heat gain to the radiation incident on the collector, okay, which is nothing but QU by AC into IT. So, here we have used AC. Okay. As I said, this collector area is 15 to 20% more than AP. Okay. That is how it is more, and this is the absorber area, right. So, sometimes we need to define this in terms of AC, and sometimes we can define in terms of AP, right. If for example, this collector, we are not collecting any heat from this FPC. Okay? No heat is collected, means no useful heat, but solar radiation is falling. Okay? So, if no heat is collected, but solar radiation is falling on the flat plate collector, then what will happen? This QE will be 0. Okay? So, under that condition, what will happen? Instantaneous efficiency will be 0, right? But already you know this QEV is AP into S minus QL. Okay? So, if this part is, this is the energy balance equation, already we know on the observer plate when we write the energy balance equation. So, this part is 0, means APS is equal to QL. Okay? So, that is why if Q is 0, efficiency is 0, in this case observer plate attains a temperature such that APS is equal to QL. So, the amount of energy what is received in the observer plate is equal to the loss, no energy is utilized, right. So, this temperature is the highest that the observer plate can attain and is sometimes referred to as stagnation temperature. Okay? That is the maximum temperature attained by a flat plate collector, right. So, what is the significance of this stagnation temperature? So, this is an useful indicator for comparing different collector designs. So, once we know the stagnation temperature of a particular flat plate collector, we can compare the performance with the others, right. Also, this is helpful in choosing proper material for construction of collector. Okay. So, this stagnation temperature plays a key role in comparing the flat plate collector as well as selecting the right material for right collectors. Okay. So, these two parameters are very important as far as performance analysis of a flat plate collector is concerned. So, now let us summarize what we have discussed in this class. So, initially we have classified the different collectors and we have learned the different components of a flat plate collectors and the kind of heat transfer fluid normally used for this kind of collectors. Okay. So, heat transfer fluid like water, mixture of water and ethylene glycols are also used when the temperature of the surrounding goes below 0 degree C. And the primary component of a flat plate collector are the observer plate, then tube, header pipe, cover, insulation, then collector box which is tilted at a swivel table angle. So, these are the primary components and how this can be installed for harvesting solar energy. And also we have studied performance analysis of a flat plate collector and we have studied transmissivity estimation based on reflection, refraction and absorption. Okay. And also we have studied the significance of transmissivity and absorptivity product. And finally, we have discussed the importance and significance of instantaneous efficiency and stagnation temperature. Hope you have enjoyed this video. So, thank you very much for watching this video.